Hi, welcome to my channel. In the previous video, we discussed about the linear SVM classification, linear SVM classification, and also we discussed about the soft margin classification, and nonlinear SVM classification, nonlinear SVM classification with the help of some polynomial kernels, with the help of some polynomial kernel, and also we are adding some additional features, similarity features. Based on this one, we are going to convert the nonlinear features into linear features and applying. We are going to linear SVM classification on the nonlinear data. So like that here, for example, support vector mission is applied on the two types of data set. One is linear separable data set, and non-linear separable data set. That means if the data is like for example here positive class are there and some negative points are there. These two points are we are going to separate into linear SVM classification with the help of some soft margin classification or what it will be. Okay, linearly we can separate these two classes into these two points into linear SVM classification, linearly separable. So this type of thing is called as a linear separable, linearly SVM classification. Okay, so this can be done with the help of soft margin classification also. Okay, and then we are going to apply the concept of non-linear SVM classification, non-linear separable data. That means, for example, here the data set contains positive points like this. Okay, positive points are like this. Okay, like it is a half-moon data set, and here we are not applying. We are unable to classify these data points by linear fashion. So at that time we are applying the non-linear fashion. So we are applying the non-linear fashion to classify this type of data set. Simply this is called a non-linear separable data. Okay. Now here we are going to apply the concepts of polynomial kernels and adding similarity features based on the existing data set. Okay. So this is called a non-linear separable data. So here in the previous we discussed about the similarity features with the help of Gaussian RBF kernel. Now we'll see what is the meaning of Gaussian RBF kernel with the help of some code. Okay. Now RBF kernel is called a phi gamma of x comma l equal to exponential of minus gamma into mod of x comma l whole square. That means x is your point that is compared with the landmark with the help of some gamma value that is equal to exponential of minus gamma into mod of x minus l into l square. Okay, this is gives the similarity between the corresponding landmark with respect to corresponding value. Okay, so like the concept of polynomial features method. That means you are going to create a new features based on the polynomial features. So like that, we are going to add a similarity features method can be used for the with many machine learning algorithms. Okay, here it may be computationally expensive to compute all the additional features. That means we are going to add new features based on the existing features. Sometimes it may be expensive. Okay, so especially on the large training data set or on the large training sets. Once again, the kernel trick does it SVM magic, making it possible to obtain a similar results as if we had added in many similarity features. So here the similarity features are adding with the help of some kernel. That kernel is called a Gaussian RBF kernel. So that is based on the phi of gamma of x comma l. X is nothing but your in that point with respect to L is nothing but landmark. Okay, we are going to find out the similarity with the instance, present instance with respect to some landmark equal to exponential of minus gamma into mod of x minus L of whole square. Okay, we find the similarity between the 2 points with respect to some landmark. Okay, it creates a new features. That's called as adding similarity features. Okay. Now, we are going to find out the similarity features with respect to Gaussian RBF kernel, where we're going to write some class. Okay, we are going to some class like SVC class classification. Now, here, the RBF kernel SVM classification equal to pipeline. So, first of all, we have to apply the standard scalar on your data set. Okay, we are converting all the features into z equal to x minus mu by sigma. We are applying this concept. Automatically the features, the original data set value convert between the -2 to +2. Okay, it in the range all the x values or y values are convert between the -2 to +2 range. That is called as a standard scalar. Then apply your classification method, that is called as a SVM underscore classification. Our model is SVC. Internally, you are providing some hyperparameters. The first two parameters is called as a kernel. The kernel is here nothing but a RBF kernel, radial basis function of radial basis Gaussian RBF kernel. Gaussian RBF kernel. Phi of this is called as phi of gamma of x comma l equal to exponential of minus gamma into x minus l whole square. Okay, here the gamma is very important. So we are specifying the gamma value, gamma equal to 5 and c equal to 0.001. So now this is the college your pipeline methods. So it contains the sequence of first of all you have to give the standard scalar, then apply your classification model. In the classification model, we are providing the two parameters, hyperparameters. One of the thing is kernel and the gamma value. That the kernel equal to RBF. After that, the model is ready. Then we are going to train with our data set. So RBF kernel underscore SVM underscore classification. This is our model. Okay. Now that model is going to be fit with x comma y. X is nothing but a features and y nothing but a corresponding class label. Like that, we are going to develop our model. So here the three things are very important. The first thing is kernel and gamma and c value. Okay, these are the three values are very important to find out our model. Okay, now here if the so here gamma equal to 5 and c equal to 0.001. So in the previous code, we are going to specify the values of gamma equal to 5 and c equal to 0.001. So for this code, we are getting the output look like this one. Okay, it contains the when the gamma equal to 5 and c equal to 0.01. So our what is our gamma Gaussian RBF kernel phi of gamma into x comma l equal to exponential of minus gamma into mod of x minus l whole square. So for here we are specifying the gamma equal to 5 and c equal to 0.001. For this values we are getting the this type of things. So here our model is separate the data points of blue color points separately and green color points separately. It creates a one bell-like structure. Okay, so it is look like a Gaussian kernel, Gaussian bell-like structure. Okay, that's why it's called this model is called a Gaussian RBF kernel radial basis function. Okay, now. So like that, we are going to change the values of gamma value and c value. We'll get the different shapes of our outputs. Okay. And now the other plots. So here the model panel shows the different plots. Okay, with respect to different values of gamma, with respect to gamma and c value. Okay. So now here the important parameters are gamma value and c value. So for this, by changing the values of gamma value and c value, we are getting different types of plots. Okay, we are going to increase the gamma value. It makes a bell-shaped curve narrower. Okay, and as a result, each instance's ranges of influence is smaller, and the decision boundary ends up being the more irregular, and also it is wingling around the individual instances. So that we are going to, sometimes we are going to increase the gamma value, sometimes we are going to decrease the gamma value. So whenever we are getting a small gamma value, it makes the bell-shaped curve wider. Okay, instances have a larger range of influences, and the decision bound ends up smoother. So like that, we're going to get the different shapes with respect to gamma values. If it is small value, it may what will happen, and it may be high value, you will get different shapes. So gamma acts like a regularization hyperparameter. It is also one type of regularization hyperparameter. By changing the values of gamma, we get the different types of shapes of the our outputs. Okay, if the model is overfitting, then we are going to reduce the gamma value. Okay, that is a very important point here. That if the model is overfitting, automatically we are going to reduce we should reduce the gamma value. If the model is underfitting, at that time we should increase the gamma value, and as well as the C hyperparameter also. Okay, so whenever the model is overfitting, at that time we are going to increase the gamma value. Like that, we have to change the values of the gammas. Okay, so other kernels exist, but are usually much more rarely. Okay, some kernels are specialized for specific data structures. Okay, like for example, string kernels are there. Those are sometimes used for the when classifying the text documents or DNA sequences. So, for example, using the string subsequence kernels, there are different types of kernels are there. One is a string subsequence kernel, or kernels based on these kernels are based on the Lewis-Distance distance method. So it identifies the similarity between the two strings. Okay, it identifies the distance between the two strings. Simply that is called as a Lewis-Distance distance. So like that, there are different types of kernels are there used for the specific purpose. Okay. Now with so many kernels to choose from, how can you decide which one is to be used? So that means here there are different types of kernels. So which kernel you are going to use at what time, that is very important. Okay, as a rule of thumb, you should always try to use the linear kernel first of all. First of all, you have to choose the linear kernel. Okay, then remember that so here linear SVC is much faster than the SVC kernel equal to linear kernel. So always you have to use the linear SVC first of all. If it is okay, then go for the kernel part. Okay, then especially if the training set is very large, especially it is a very large, or if it has plenty of features, okay, then at the time you have to always use the linear kernel. So if the training set is not too large, okay, if the training set is not too large, then you should always also try the Gaussian RBF kernel. That means if the dataset is large, then go for the first of all you have to execute the linear SVC. Okay, if the training set not too large, then you have to try the Gaussian RBF kernel. It works well in the most cases. Okay, so many kernels are there to choose from. How can we decide which one is used? Then if we have time and computing power is there, then we can experiment with a few other kernels using the cross validation, with the help of cross validation and the git search method. So suppose then you should want to experiment with like that, especially if there are kernels specialized for your training sets, data structures. Okay, like that there are different types of kernels are there. Okay, we have according to your situation, you have to change the different types of kernels. Okay, based on your time and based on your computing power, based on your experiment like that, you have to follow different types of kernels. Okay, this is about the Gaussian RBF kernel. So in the next video, I'm going to discuss about the computational complexity of all the different types of SVM classification techniques. Thank you for watching our video. If you like the video, please subscribe. Thank you very much.